This is your video on hybridization, okay? It's kind of a complicated, but not too complicated topic, so I'm probably gonna do it in more than one video. So look for part 2, maybe even part 3, but probably just 2 parts. We're gonna see if we can get through it in 2. Okay, so what is hybridization? It is the process by which atomic orbitals are mixed to form new identical orbitals. Okay, pretty simple. If you kind of know what hybridization is in the first place, think about a hybrid car where you have a gas-powered car mixed with a electric car in one car. And sometimes it can run on gasoline, sometimes it can run on electricity. It just depends on which one you choose, right? So, but it's a mixture of the two. That's the same idea that we're doing here. But in order to touch on this topic, we have to kind of go back and look at some Lewis dot structures and electron configuration, okay? So Lewis dot structure focuses on the valence electrons. So in nitrogen, you know that it's in the group 15, so it has 5 valence electrons. And it doesn't really matter how you put it, but usually you put one on each side and then you double up. That's pretty simple. So if you look at it, it looks like you have 3 spaces for an atom 3 spaces for bonding and 1 lone pair. If you look at fluorine, it's in group 17 and it has 7 valence electrons. So if you look at it, it looks like it has 1 bonding area and 3 lone pairs. We know that's pretty true, right? It works pretty well, okay? But now we look at carbon, and it's in the group 14, so it has 4 valence electrons, and it makes 4 bonds, okay? No lone pairs. Well, one of these things, there's a little bit of an inconsistency. Right now, these are pretty consistent, but in carbon, there's a little bit of an inconsistency that I want to kind of clear up with, and this is why we have hybridization. If you go back to electron configuration, what is the electron configuration for carbon? Well, if you know from electron configuration, you start thinking we're going to start with 1s, and it has 1 orbital. Okay, after that it goes 2s, and it has 1 orbital. Then you have 2p, and it has 3 orbitals. Okay, and if you know, remember how many electrons can go in each orbital? Okay, just 2, right? But carbon has 6 electrons, so we have 1 here and 1 here. Oops, I went the wrong direction with this one. Sorry about that. I should be going this way. Okay, and then we have 1 here and 1 here, and then we have 1 and 1. Okay, now according to this configuration, if you look at it, it looks like it only can make 2 bonds. And that doesn't really make sense, right? Because we know it can make 4 bonds. So why is this inconsistent? Well, there's a reason why. Because, well, let me back it up. You know that this is inconsistent because 1 electron can make another bond because it can bring in 1 more electron from somewhere else. This one doesn't have anything there, so it can't make a bond, according to this. So what do? Well, we have to make a hybrid of the orbitals. So, how do we correct this? How can we make this correct? Well, we're going to make the hybrid. So what we're going to do is we're not really going to focus on this at all because that's an inner electron. And when we make bonds, we're not worried about the inner electrons. We're only worried about the valence electrons. And if you can remember from when we did electron configuration, the S and the P, the highest S and P orbitals are the only ones that can that are the valence electrons, right? That was kind of our definition of it. But we are going to mix these 2. So if we mix these 2, we're going to kind of like squeeze these 2 sublevels together and make a hybrid of it. So we're going to end up with 4 orbitals. How many orbitals do we take from this S level? Just 1, so we write an S. Anytime in science we see a letter, it's like math, we know there's like 1 there. And then we took 3 from the P level, so we do 3P. So this hybrid is sp3. Now, how do we write this? Well, if you remember from back in electron configuration, we had the three rules. We had aufbau, means you had to fill up from the bottom up, and then you had polys, which said you had to go in different directions. But then you have Hund's rule, which says everybody gets one before we double up. Well, when we hybridize, we still do the same thing. We take these 4 electrons and we put them in here. So we have one going this way, another one here, another one here, and another one here. That takes care of all 4 of those electrons. Now, this configuration looks like this. Each one of these can bring in another electron to make a bond. So if I were to make carbon with hydrogen, hydrogen has one here and hydrogen here. Well, then we can make one here, 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 and here. Just like what we said, and I'm running out of board space, sorry. Okay, so that's kind of the concept behind hybridization. We're going to take these 2 sublevels and we're going to squeeze them together and use them as one hybrid orbital to make this work so that it can bond. So we're sharing more so, okay? Now, how does this translate into compounds? That's where we're going next, okay? So that's where I'm going to go with it next. How do we translate this into a compound? All right, well, let's take a look at this. Let's take a look at if we have CF4, okay? We're gonna have CF4. So we take carbon, which has, I'm drawing a blank here. We have carbon, and it's gonna bond up to fluorine, okay? Now, if we're focusing only on the carbon, we know that fluorine looks like this. Well, there's actually one here, and they're sharing. Wasn't that what's happening here? Right here, sorry. If we go, here's fluorine's electron, fluorine's electron, fluorine's electron, fluorine's electron. Oops, too big. So that's exactly what's going on, okay? Now let's take a look at how this works in with nitrogen. And oh, I forgot to tell you something. I'm going to come back to it in just a second because I got to erase this. But I want you to write something down for me. Okay, I want you to write down this sentence, and I'm going to say it twice. Only two things hybridize: a sigma and lone pairs. And in a sigma bond is a bond made, the first bond made, okay? And lone pairs. Those are the only ones that can hybridize. And if you think about sigma, they're a single bond, okay? So kind of put that on there just as like a clue that it's a single bond, just one bond, okay? So in the next video, I will put down the definition for a sigma and a pi bond, but I'm going to mention them now. But a pi bond is a double bond, so I'll put them up there in a triple bond. So I'll put those up there. But how do we represent something like ammonia? Okay, NH3. If you can remember how to draw that, go ahead and draw it. But if you remember how to get the math of this, this has 5. Each one of these has 3. Has 1. So we have 8 valence electrons. So you end up with N. Oh, sorry. Let me move this around. H. I can't even draw today. Sorry. I have it on my paper. Okay. NH3, which is ammonia. Not ammonium, because that's something different, but ammonia. And I would memorize that because it does come up a lot in the future. Okay, so how does this represent electron configuration versus hybridization? Okay, so if you remember, and I only want to know what the hybridization is of nitrogen. Okay, just the nitrogen, not the hydrogen. Well, if I know the electron configuration of nitrogen, it's similar to carbon, but a little bit different because it has one more electron, right? So we have 1s, 2s, and then we have 2p. So nitrogen looks like this: up, down, up, down, up, 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 down, Did I do that right? No, I did something wrong here. 2, 4, 7. Okay, I think now I got one too many in there. There we go. Sorry. I had one too many. I was just going a little stir crazy there. Okay, so here's what we have. Okay, so we're looking at this nitrogen, right? It looks like we have 3 bonding pairs and 1 lone pair. Down here, how does it represent? Well, if we hybridize and squeeze these 2 together, okay, so we're not going to worry about this, okay? We're going to take here, okay? We're taking 1 from here and 3 from here, okay? So we're taking 1 of the s orbitals and 3 of the p's, okay? So you put in the up, down, up, up, up. Well, this is a perfect representation for this, correct? So now we have an sp3. So this has an sp3 hybridization, okay? And that's pretty much what we're doing in this video. Okay, I know you're gonna come with a lot of questions. Hopefully I'll answer some more in the next video, okay?